Yeah, hello everybody, and today I will start with one first research question, that is if we have any signs of divergence in the Italian Holstein. This is going to be my main topic. But then, since we are working and trying to address some questions that you have already heard a lot from the other presenter as well, we are also working on how to measure inbreeding, both based on pedigree data as well as genomic data. We are trying to see the effect of genomic selection in the inbreeding trend, as well as we are starting to work on some inbreeding repression evaluation to measure the effect of inbreeding in some traits. But let's start with the main topic of today, so the divergence in the breed. And as you heard already from Professor Cassandro, the Holstein is the most widely spread breed in Italy. It counts over 1 million animals. So, well, this is something that is quite similar to other reality in Europe as well. But what makes the Italian Holstein pretty different from what we see in other countries is that the use of the milk is then completely different. We have that 80% of the milk is used to cheese production, and only 20% of it is instead used for direct consumption. On top of that, we have that Italy is the country with the highest number of PDO cheeses, over 50 PDO cheeses. But then when we look at the production volume, then only three ripened cheese produce over 80% of the total production in terms of cheese making, which are the Grana Padano, Parmigiano Reggiano, and Asiago. I put Trentin-Grano in bracket here because is a specific denomination that we have within the Grana Padano that, well, we are going to talk about it a bit later as well. So let's start with those very big three main players, the Grana Padano, which is the biggest consortium in Italy. It originates from Chiara Valley Abbey in Milan, and it has quite an old history. They started to produce this cheese already in the 12th century. They spread around the world. They produce more than 5 million wheels per year in 2021, and we can produce this cheese in 34 provinces in 5 Italian provinces, regions in the north of Italy, mainly located across the Po Valley region. The Trentin-Grana is a peculiar example within the Grana Padano consortium because although it's really small portion of the total production in the Grana Padano, only 3% of the whole production, has very peculiar ways of breeding the animals, and there is a very close connection between the origin and the traditional farming. The animals are exposed intensively to pasture condition, which is not quite common in the other realities. The Parmigiano Reggiano is another example of ripened cheese with a very old tradition. Middle Ages by Benedictine monks, they started to produce this cheese. Very big production as well, 4 million wheels per year. And there is, again, a very, very close link between the production of this cheese and the area where this cheese can be produced. Only 4 provinces in the Emilia-Romagna region, where indeed more than 90% of the milk is used to produce cheese in this area. And 1 province in Lombardy as well, Mantova. Finally, with the for the last consortium we are talking today is the Asiago. This one is a bit different example. Initially was made from sheep milk during the 11th century, but then they started in the 16th century to use bovine milk as well. They have a lower cooking temperature compared to Parmigiano Reggiano and Grana Padano, and there are 2 different versions, the fresh and the aged one. Again, here, close link to the area of production, only 4 provinces in Veneto and Trentino. And well, across this rich variety of dairy products made in Italy, the most widely reared cow is the Italian Holstein. So then, based on the hypothesis that consortia-oriented selective breeding can cause divergence in animals originated and bred in different situations, but still from the same breed, we wanted to evaluate the presence of differences in terms of genomic background of those animals. So how we did it? Well, we started with a pretty big data set provided by the Anafi BJ, and we started to filter those data to fulfill some criteria. First of all, of course, the area of breeding. And this one was chosen based on the consortia I just mentioned to you. And then we filtered for chip density, because we were working at the end of the day with imputed data. So we wanted to be sure that at least the genotype panel that was used firstly for the genotyping was at least medium density, 50K. Then we also filter for the age of the animal. We didn't want to have any confounding effect for the generation of belonging of the animals. So then we only looked at last generation, the latest generation. And then to have a sample that was more heterogeneous as possible in terms of the different farms, we only selected at maximum 10 cows per each farm. The method that we used to detect divergence. So firstly, we used the Bayesian information criterion, BIC analysis, to check whether the hypothesis of presence of subpopulation could be a reasonable hypothesis in our data. Then we use the discriminant analysis of principal component to detect and evaluate the divergence found in the population. And finally, we did a pairwise external validation, so with a calibration and a validation set, to further evaluate the pairwise differences among the subgroups evaluated. So in the end, we had 1,000 cows filtered in for the filters I just show you. Those animals descended from a total of 400 sires, and already looking at the sire side, we could see some pretty interesting results. So we found that 70% of the sires were found specifically in one subgroup only. So this is already a small sign that perhaps something is going on in the selection of those animals within each consortium. And then the sire nationality. Then we have 57% that were from US and Canada, and 43% that were from Europe. So let's start with the first result, the divergence analysis, the Bayesian information criteria. So in this analysis, no group information as prior information, but just we wanted to estimate the presence of cluster, that we call it here K. So we ran the analysis from subgroup 1 to 20, and well, these results show the best model fitting, that is around 7 potential subgroups. Although when we look at the strength of those results and looking then at the pairwise delta BIC, we found that there was quite strong evidence of presence of cluster until 4K. Delta BIC was higher than 2, but then it becomes smaller and smaller until it reached 7 cluster. All in all, these results allowed us to say, well, perhaps there might be some divergence going on. So the presence of subpopulation appears to be a reasonable hypothesis. So then we continued with the discriminant analysis of principal component. Here you can see the plot of the LD, so the linear discriminant function 1 and linear discriminant function 2. And well, indeed, there might be some differentiation within the groups, especially for the Trentingrana animals, the animals that belong to the Trentingrana. And overall, when we calculated the reassignment accuracy of this analysis was 76%. So we had 239 cows that were misclassified by the model. And this percentage quite varied a lot in the different consortium. 68% for the Grana Padano one, and it reached 84% in the Trentingrana then. So again, the Trentingrana seems to be the one that differentiated most. Finally, for the external validation, where we then further looked at the pairwise comparison, so 2 groups each. And then we used this validation set. So we used 80% of the animal in the calibration set, 20% in the validation then. Well, unfortunately, it's a bit blurry, this slide, but well, anyway, I just wanted to highlight those 2 results. The comparison and the accuracy that we achieved comparing Parmigiano Reggiano and Grana Padano was, well, not so high, 60%, but then the comparison between the Asiago and the Trentingrana was pretty high also in the validation set, 81%. So all in all, this study provided preliminary evidence of genomic divergence within the Italian Holstein breed due to its use in different dairy production. And then, well, this question comes to our mind, how we can use this information in the future. Could we design some specialized breeding scheme, but maybe we are then reducing even further the variation that we have within each specific cluster. So this is something that we still have to work on it. And of course, if you want to have some further information, we just published this paper in, well, last year actually. So just for further information, here is the paper. So let's go then with a few more research questions that we are going to address today. And we are going to start with those 2. So we, again, wanted to measure inbreeding, both based on pedigree level and range of homozygosity data. And we wanted to evaluate the trend of inbreeding, especially looking at the pre and post the introduction of genomic selection. So how we did it? Here we worked with a much bigger data set, also provided by the ANAFI-BJ. We were working with more than 70K animals, Italian Holstein dairy cows. From this plot, you can already see the trend that was already shown quite a lot this morning. The genotype animals really increased a lot after 2010. And what we did was then using both genotype data and pedigree data, we calculated the inbreeding based on those 2 set of data. We also calculated the complete generation equivalent as a measure of how complete and depth is our pedigree. And we use this measure also to evaluate whether the pedigree depth has an effect in the correlation that we have between the 2 measurements, pedigree and genotype data. So this is just a very, very short overview about the results we got on the range of homozygosity analysis. So here we have on the x-axis the chromosomes, and on the left the row counts, and on the right the average rows in terms of the length. So, well, all in all, we found that there seems to be like a pattern in the row counts depending on the chromosome length. This was something expected. So chromosome 1, longest chromosome, more rows as well. But then there seems to be something also quite interesting, especially on chromosome 10. There seems to be quite a lot of range of homozygosity, as well as the length was pretty high, the highest. Well, no, with 20 were the highest, more than 3 megabases long. So perhaps here there is a bit more room for some signature of selection studies. But then just have a look on the results we got for the inbreeding then. Here we have two violin plot on the inbreeding based on the two measurements, runs of homozygosity and pedigree. And then we compare those results with like a reference value that we found online, 0.08 average as an average value in the Holstein population based on pedigree data, and calculating it in over 1 million animals born in 2019. So this is actually our baseline value. And well, when we compare this value with what we found in the Italian Holstein, well, if we compare it with what we found at pedigree level, nothing really surprising, quite similar value, and only 24% of our animals are above the threshold that we found as reference value. But then, if we compare instead what we got based on runs of homozygosity, we have completely different picture. So like more than 90% of our animals are above this threshold. So this is just to stress a bit that depending on how we measure inbreeding, we might have really completely different picture. Yeah, similar for the highly inbred animals that we considered as the one that had an inbreeding value equal to the mean plus 3 standard deviation. The numbers were similar, but then only 23% of them were exactly the same. So also here, different, depending on how you measure inbreeding, you might have completely different picture. And then we calculated the correlation between the two measurements, runs of homozygosity, inbreeding based, and pedigree. We wanted to include the CGE as a potential factor that might have an impact in the correlation. And indeed, although the average CGE was quite high in the entire data set, equal to 10 CGE, which is quite remarkable. Still, when we divided the animals with CGE lower than 10 and higher than 10, the correlation between the two measurements was quite different. And all in all, we have a correlation between them equal to 0.68, which is quite similar to what we found in the literature as well. Another aspect that we evaluated was the generation interval. And well, in general, it dropped quite a lot from 7 years to 3, which is again what we found also in other Holstein population. And we found specifically 2 main reduction, and again, nothing surprising. The first one might be due to the introduction of the blood evaluation, and the other one due to the introduction of genomic selection. So then, since we had chronological data, we also wanted to evaluate the inbreeding trend based on the 2 measurements. And just to make this story really short, we had that for both measurements, the inbreeding seems to increase per year. And actually, when we calculated the delta F, not per year, but per generation, for both methodology, we got delta F per generation that is higher compared to what FAO suggested as a limited value for not reducing too much the genetic variability in the population. Finally, as you heard already from the previous presentation, we also wanted to try to dig more on the role of genomic selection in the reduction of genetic diversity. So then the exact similar plot, but the same plot as before, but then dividing the period in when there was only progeny test selection, the transition period, and then the progeny cross genomic selection. And well, similar results in the Italian Holstein as well. The relative change in delta F is high. So this means that we have an acceleration, not only an increase throughout years, but also an acceleration of the delta F in the genomic era compared to the previous one. So to sum up what we found here, we found moderate level of inbreeding based on the two methodologies. There were some rows differentiation among chromosomes, so there might be some room for signature of selection studies, and there seems to be an acceleration in the rate of inbreeding after genomic selection. So let's conclude with the final question of today. Do we have sign of inbreeding depression? So, and how we did it? So we started to the same data set as before, but then we had, of course, to evaluate which animal had phenotype data as well. So we were looking for animals with production, fertility, and functional traits. Today, I will just talk briefly about the results we got so far for the production trait. So days in milk, fat and protein yield in kilograms per lactation. So what we did, of course, we had to calculate inbreeding estimation, again, as I showed you before. And then we developed some mixed model to try to account and evaluate the effect of inbreeding. So those are the factors that were always included in the model: the interaction between the herd and ear, the month of calving, the parity, and the random effect of the cow. And then we try to include the inbreeding based on three different methodologies. First as beta coefficient, and then we divided the inbreeding based on percentile classes. And finally, as you heard from Professor Malteca, there seems to be a few differences among the length of the runs of homozygosity that we have in terms of the effect that might cause in the animal. So then we also wanted to divide the inbreeding based on runs of homozygosity by length classes. So just very shortly, the first part of this slide show the results we got for the inbreeding based on the two methodology in this subset of animals. And then the second part is instead, it regards the percentile classes that we calculated. We calculated 7 percentile classes, which means that roughly each class represents 14% of the distribution. And for the last model, since we know that indeed, first, the length of row runs of homozygosity might have different meaning, and also the age is a, the length might have an explanation in terms of when the inbreeding happened, the expected age of inbreeding, and this was what we follow based on a previous study by Dokes et al. We divided F row in 5 length classes, starting from row class 1, the shortest one. So this means that perhaps there was a reduction in the genetic variability over 20 generations ago, whereas the longest class, 16 to 32 megabases, these might be signs of more recent inbreeding, less than 5 generations ago. So let's go to some of the results we got. So overall, in the first model, where we included the inbreeding as beta coefficient, we found that as for each 1% increase in the inbreeding, we got a reduction in kilogram of milk per lactation, as well as kilogram of fat and kilogram of protein. And if then we looked further on the differences between expected phenotypes of cows with low and high inbreeding, 5% and 95%, these results becomes even more clear. And if we want to put this value in a more practical sense, and we know that the average milk production in the Italian Holstein is roughly 10K milk per lactation. And if we want to translate the result to a Parmigiano Reggiano breeder, then this might cause a roughly 1 wheel loss per lactation per cow. When we included the inbreeding as percentile classes, we found actually very similar results. The only thing that we can maybe highlight here is that when we included the inbreeding based on runs of homozygosity, we could see much more easily the differences among each percentile classes in terms of reduction of kilogram of milk, which was not so clear instead when we included the FPED in the model. Very, very similar results also for the kilogram of protein and kilogram of fat. So finally, when we divided FRO based on the length classes, then we found results that were quite nicely aligned with the literature, so that there seems to be not significant effect for runs of homozygosity that are short, whereas there seems to be something going on in runs of homozygosity that are quite recent, so longer ones. And again, very, very similar results for a kilogram of protein and a kilogram of fat. So to sum up, runs of homozygosity measure of inbreeding seems to be more effective than FPED to evaluate the effect on yield traits of each percentile classes. The effect of inbreeding depression was more evident in the highest inbreeding percentile classes, as well as the inbreeding at recent generations seems to be more harmful than inbreeding at distant generation. So what to do next then? Well, something that we would like to do and to dig more into it is to confirm genetic divergence also at international dairy chain level, so not only in the context of Italy. We would like to include the results that we found so far in novel tools and application for breeders. And finally, we are working on evaluating the effect on of inbreeding at more sustainable traits like resilience. And with that, I would like to thank you for listening.
Is there a question? So can you show us a class of other weights that you created?
Yes. Oh, no. No. So let's see.
Can you also repeat the question that you got?
Yes, I will. That's no, wait. Here. Yes, so the question was about how we divided the runs of homozygosity in length classes. And
so my question was, why did you truncate at 32 megabases? Average.
Yeah.
Was that the largest?
Yeah. So the question was why we truncated on 32 megabases. Well, I think we did it to strictly follow what they explain in this article, but also because I have to say that when we work with imputed data, there's sometimes animals that they really show super high level of inbreeding, such a long row that we don't really trust them so much. So then we decided to truncate at the 32 megabases.
Thank you. There is a question. Always by Gustavo.
Gustavo is asking what will be the new tool to manage inbreeding. I think that could be to you, or it can be to the others.
Perhaps I would like some help as well. But yeah, well, what we are, so for instance, in the Italian reality where we have, there seems to be some divergence going on. One way to go might be to have more specialized breeding goal depending on the different consortium. So then in this way, of course, we are reducing the genetic variability within each consortium, but overall we are increasing then the variation among the Italian Holstein. So this might be a way to go, but also like using optimal contribution selection, of course, is something that we have to take into account. Yeah.
Can I?
Yes.
At the end, in the middle of your presentation, you say that roughly 1% of inbreeding will mean losing one wheel of Parmesan. Mm-hmm. Is that per cow per lactation?
Well, no. So this one. So this is the result comparing the two most extreme in the distribution. So animals that are having a inbreeding that is in the fifth percent lowest and 5% highest. So then this result is comparing those two extreme, not 1% only increasing the inbreeding. So it's more
per cow per lactation.
Yeah. It's per cow per lactation. Yeah.
100 cows, 100 wheels.
Yeah. All inbred.
Every
yes.
Lactation.
If they are all inbred. Yes.
Of course.
Yes.